In this video, I'm going to show how we can use those kind of more specific formulas that we found in the last few videos, and then kind of compare that work to the general chain rule. And then I'll leave it up to you to decide, do you want to use these specific formulas that we've established, or are you more comfortable using the general chain rule, that four-step process that we've kind of been using so far this chapter? So let's look at some derivatives. First up, I've got y equals e to the 2x power. And first thing you want to do is identify, do I even need the chain rule? And when we're working with exponentials like this, e to the 2x, you want to pay special attention to your power. Here I've got 2x. If your power of e is anything more complicated than just x, so here I just have 2x. All I have is a multiple of 2. I have to use the chain rule. So this is definitely going to be a chain rule problem. The next thing I want to identify is which of the three cases does this look like. Exponentials, I think, should be easier to pick out. This, to me, looks like y equals e to the u power. So we said if you're working with y equals e to the u power, the derivative of that is u prime times e to the u. So let's look at this formula. Let's see what it says. U, remember, is your power. So when I say u prime, what I really am saying is the derivative of the power times e to the u. This is exactly the same, and hopefully we kind of feel a similarity between e to the x, right? Remember when we were taking the derivative of e to the x, that part of our function stayed exactly the same. So when I take the derivative of e to the u, this part of my function stays exactly the same. We just have this extra multiple of u prime. That's really all we're doing. So when I go to find my derivative, all right, I'm going to say multiply by my power, derivative of 2x, that'll be 2 times e to the u. Well, e to the 2x, that part stays exactly the same. And there's my derivative. It's as simple as that when we're using this formula. So I think having this memorized is a really nice tool. It speeds up the process of finding the derivative and using the chain rule a whole lot. I do think it makes these problems much easier. Next up, I have f of x equals natural log of x squared plus 9. Again, you want to look at what's inside of your natural log function. Here I have x squared plus 9. If you have anything more complicated than simply just natural log of x, I have to use the chain rule. So this x squared plus 9 is a really big hint that we're going to have to use the chain rule. So I'm now going to identify which of the formulas I want to use. I see this natural log. I say, boy, that looks an awful lot like y equals natural log of u. Okay, well, if our function looks like natural log of u, we said that our derivative is simply just u prime divided by u. So u is just whatever's inside of your natural logarithm. Remember, that's your kind of inner function. So this says I take the derivative of what's inside of my natural logarithm divided by whatever's in my logarithm. So when I go to find my derivative here, f prime of x, I say, okay, derivative of x squared plus 9. Well, the derivative of x squared plus 9, that will be 2x divided by u. I'm going to leave this part exactly the same, divided by x squared plus 9. And then, yes, if you can go ahead and simplify it, then absolutely go ahead and do that, but this is about as nice as it gets. So there's my derivative. So it's much faster, again, if we use this formula. I think it does just save a whole lot of time. Y equals x to the 4th times natural log of x. Again, the very first thing I want to do is establish, do I need to use the chain rule here? So I say, okay, well, this kind of looks like the last example we did. We have a natural log function going on here. But remember I said you need to use the chain rule anytime you have something more complicated than just x inside of your natural logarithm. Here I just have natural log of x, which means I don't have to use the chain rule. You could, I guess there's no harm in using it, but there's really no benefit to using it either. I look at this, I see x to the fourth times natural log of x. This was kind of a trick question thrown in there. This is not a chain rule problem. Instead, this is a product rule problem. So keep an eye out for when we need each of these derivative rules, because on quizzes and on exams, I won't be telling you, hey, use the product rule or use the chain rule. It'll just say find the derivative, and it's up to you to decide what rule you need to use. So let's go and use our product rule real quick. Our derivative, let's take the derivative of x to the fourth first. That'll be 4x cubed times natural log of x, plus this time x to the fourth will stay the same, x to the fourth, times the derivative of natural log of x. That will be 1 over x. And then we can simplify this just a little bit. We'll have 4x cubed natural log x plus x cubed. If you want to, again, we've got a common factor of x cubed. We could factor that out. I'm not going to ask you to do that. I'm not going to take points off if you don't, but I think it's just a good habit, good practice, if anything. So x cubed times 4 natural log x plus 1 is what I'd be left over with. And hey, there is my derivative. So not every problem we see in this section, and not every problem needs the chain rule. Sometimes we need it, sometimes we don't, just like the product rule, just like the quotient rule. Last one here, g of x equals 5x squared minus 9x plus 1 all to the 7th power. Again, look for those parentheses and look for something more complicated than just x to the 7th. So here I have a whole function raised to the 7th power. So to me, this looks like y equals u raised to the nth power. I think these can be the trickiest to pick out because we don't have a natural log, we don't have e. It's perhaps a little bit more subtle here. But we said, hey, if you're working with y equals u to the nth power, when you go to take the derivative y prime, we essentially just use our power rule right here. So we multiply by our power and subtract 1 from our power. So n times u to the n minus 1. We just have to multiply by u prime, the derivative of that inside part. So when I want to find the derivative, g prime of x, I'm essentially going to look at this part right here, and I'm going to say, okay, I'm going to start by multiplying by my power. So this is 7. Actually, let me give myself just a little bit more room. G prime of x is equal to 7 multiplying by the power. U, this part stays the same, 5x squared minus 9x plus 1. That inside part's actually going to stay exactly the same. So let's see, we'll leave that as 5x squared minus 9x plus 1. That inside part stays exactly the same. Then we subtract 1 from our power. So I'm subtracting 1 from 7, should be to the 6th power, times, I still need to multiply by u prime. Hopefully we're feeling like we're remembering to do that at this point, because in every single one of these problems we're multiplying by u prime. So I need to multiply by u prime. That's the derivative of this inside part right here. So the derivative of that inside part, that would be 10x minus 9. And then at that point, I'd probably just leave my answer like this. If you really wanted to, you could distribute the 7, but you'd have to distribute it to the 10x and to the 9th. You can't distribute it to this part right here because of this exponent of 6. So to be honest, I would just leave my answer like this. And I would say, you know what, there is my derivative, there is g prime of x. Let's look at one more example before we wrap this video up. Just, coming back to the old classics of problems. Here I want to find the derivative f prime of x, and the values of x where the tangent line is horizontal. Same stuff we've been doing, right? We're just maybe throwing in the chain rule here. So here I've got f of x, 3x plus 1 to the 4th. I want to identify, do I need to use the chain rule? Or what derivative rules do I need to do? Here in this case, I've got 3x plus 1. That's more complicated than just x, right? I've got a function raised to the 4th power. This is definitely going to be a chain rule problem. So this looks like y equals u to the nth power. We said the derivative of that was n times u to the n minus 1. We just do our power rule, times u prime. So when I go to take the derivative of this function, f prime of x, I'm going to multiply by my power. So this is 4. Remember u, this inside part, this stays exactly the same. That's still going to be 3x plus 1. So 4 times 3x plus 1, subtract 1 from my power. So now I have to the third power, times the derivative of this inside part right here, times the derivative of 3x plus 1. Remember, that's our u prime. So derivative of 3x plus 1, that'll be 3. And then that's it. We simplify if we can. Here, 4 times 3, we can simplify that. So why not? This is 12 times 3x plus 1 raised to the third power. So this is my derivative. So we found f prime of x. What else do we need to do? We need to find the values of x where the tangent line is horizontal. Again, we're using a different derivative rule, right? We're using the chain rule, which is kind of a new idea. But at the end of the day, we're still doing the same thing that we've always been doing. We're finding derivatives. Derivatives, even though we're using the chain rule, derivative still tells us the same piece of information. Still tells the slope of the tangent line, still might tell us velocity if we're working with a position function, tells us rate of change. So when I say the values of x where the tangent line, so first of all I'm thinking about f prime of x, is horizontal. Remember, the tangent line the slope of the tangent line is given by the derivative, and here I want a horizontal slope, so I want the derivative to be equal to 0. So I'm going to take this derivative that I just found right here and set it equal to 0, solve for x. So I'm going to take my derivative, which is 12 times 3x plus 1 to the third power, set my equation equal to 0, and solve for x. So we can divide by 12 pretty quick. 3x plus 1 to the third power. Dividing by 12 still has 0 on that right-hand side. We need to get rid of this exponent next, so why don't we take the cubed root of each side? But the cubed root of 0 is still just 0. So I've got 3x plus 1 equal to 0. This is, from here on out, just a little bit of algebra, so 3x equals negative 1. At x equals negative 1/3. So at x equals negative 1/3, I'm going to have a horizontal tangent line. So that's where I might have that horizontal tangent line. Could look something like that. Could also kind of look something like this as well. That's not a great picture, but these are things that we're going to want to keep in mind in Chapter 4, because this idea of having a horizontal tangent line is going to be really, really important. It is something that we're going to pay very close attention to in the next chapter. And in the next video here, we're going to try and put together all of the derivative rules that we've talked about. So we're going to look at some examples that use the product rule, the quotient rule, and the chain rule, and some examples that involve all of those. So examples that maybe use the product rule and the chain rule, or the chain rule and the quotient rule. So we'll be adding in these different combinations of derivative rules which we might see from time to time.